Share screen. Everybody can double check you're muted since I do hear a little background noise somewhere. Okay, and okay, so I'm just going to pull up some notes and then we'll get going. There we go. Okay. All right. So I'll start with a quick recap of last time where we saw Friedwald's algorithm. All right. By the way, can someone confirm you can hear me and see my screen?
Yeah, all good.
Great. Thank you. Okay. So yeah, this recap will just take like 3 minutes. So the input to Friedwald's algorithm is three matrices A, B, and C, and their entries come from some field F. So they're each n by n matrices over the field F, and the goal of the algorithm is to determine whether A times B equals C. Okay, and so you can think of C as being provided by an untrusted prover who's claiming that C equals A times B, but might be lying. So the algorithm's goal is to ascertain whether or not that claim is correct. And the way the algorithm works, at least the variation of it that I presented, is the algorithm just picks an R from the field at random and checks whether C times, I'm sorry, I forgot. So it sets X to be the vector of the first n powers of R. And it checks whether C times X equals A times B times X. And the key point from an efficiency perspective is that you can compute A times B times X with just two matrix vector multiplications. So CX is one matrix vector multiplication. Computing BX is another matrix vector multiplication. And then multiplying A by that result is yet another matrix vector multiplication. So the total runtime of the algorithm is the time to generate X and do three matrix vector multiplications. And this, the total time for that is order n squared field operations. And so note that this is much faster than computing A times B explicitly, like from scratch. Okay. Right. So if this algorithm, just did not have access at all to an untrusted prover and it wanted to know A times B, it would have to compute A times B on its own. And the fastest known algorithms for that take way more than n squared field operations. But if an untrusted prover provides a matrix which is claimed to be A times B, and the algorithm merely needs to check whether the claim is accurate or not, you can do it with just n squared field operations. So much faster than if there was no prover. If everyone could double check one more time that you're muted, I'm hearing a little more background noise. Great. So that's the algorithm. So again, checking whether a claimed answer to this problem is correct is much faster than any known algorithm for computing the answer from scratch. And as we discussed last time, you can think of C times X as like a row-wise Reed-Solomon fingerprint of C. And similarly, A times B times X is like a row-wise fingerprint of A times B. And if C and A times B are not the same matrix, then there must be at least one row where they don't have the same row. And then, the whole point of Reed-Solomon fingerprinting is that if you fingerprint two different vectors with overwhelming probability, you get out a different fingerprint, a different result. And in that case, the row by row fingerprint of C times X will not equal the row by row fingerprint the row by row fingerprint of C will not equal the row by row fingerprint of A times B. Okay, so just the final statement in this review. So formally what we showed is that if the matrix C is not equal to the true product matrix A times B, then the probability over the random choice of R from the field that C times X equals A times B times X, where remember X was the powers of R. We saw that probability was at most n-1 over the size of the field. Okay. In summary, the algorithm is sort of, rather than explicitly computing A times B, it's merely computing a row by row fingerprint of A times B, and that fingerprint can be computed much faster than computing the full matrix A times B. And the fingerprint is enough to check this equality with overwhelming probability. Okay, so that was last time. So today, I want to cover the Schwartz-Zippel lemma, and I'll say what that is in a moment. I want to discuss a little bit about error correcting codes. Okay, especially something called the Reed-Solomon code and something closely related called the low-degree extension codes. Actually, sometimes these are used as synonyms for each other. And then I'll talk about univariate Lagrange interpolation. And this might be it because I do want to keep today to an hour. But if there's time, we'll briefly, define and discuss a little bit interactive proofs and arguments. But that might have to wait till next week. Excuse me. Okay, so that's the plan. Let me just pause here and see if anyone wants to ask any questions. Okay, so let's talk about.
I have a question.
Go ahead, please.
I have a question about the equality C equal A times B.
Yeah.
I get a look at it so to check why we have the n-1. So it seems that like we are checking the equality of two matrices, and if we check two matrices, so it's a linear application. So it's checking if these two matrices are equal on the basis, any basis. So is the n-1 just let's say the n-1 vector? Two matrices can be equal at most at n-1 free vector. It's correct?
Yeah, that sounds right. Yeah, this n-1 over field size is coming in because it's treating every row of C and A times B as a degree n polynomial or degree n-1 polynomial, and two distinct polynomials of that degree can agree at most n-1 points. And there's a variation which which I mentioned last week, and I'll mention again right after we discuss Schwartz-Zippel, where rather than treating the rows as univariate polynomials, it treats them as n-variate polynomials, and then this n-1 will go to 1. So there's a variation where the failure probability, that is the probability that C does not equal A times B, yet the fingerprints match, is at most 1 over field size instead of n-1 over field size. And again, the difference is just whether you treat each row of C as a univariate versus an n-variate polynomial. Did that answer the question? Maybe it didn't. Maybe I misunderstood the question.
Thank you. Thank you very much.
Okay. Great. Okay. Other questions? All right. Okay. So yeah, Schwartz-Zippel is a statement about multivariate polynomials, and so I want to briefly discuss what it means to talk about the degree of multivariate polynomials. So now let's let q of x1 to xn be an n-variate polynomial. Okay, and let me give some examples here. So, maybe n is 3 and q is, x1 times x2 plus x2 times x3 minus x1 or something. Another example would be x1 times x2 times x3, or maybe x1 plus x2 minus, 4x3, whatever. And yeah, normally when I talk about the degree of an n-variate polynomial, I mean more specifically what people will often call total degree. And so total degree, let me give one more example. Let's make this an x1 squared here, actually. Okay, so total degree is the maximum across all monomials in the polynomial of the sum of the degrees of each individual variable in that monomial. Okay, so coming up to these examples, this would be total degree, this thing has total degree 2, because, this term has total degree 2, since it has degree 1 in x1 and degree 1 in x2, and 1 plus 1 is 2. This term also has, total degree 2. This monomial, just x1, has total degree 1, but we take the max across all the monomials, so the total degree of this thing is 2. This thing has total degree 4, because, the total degree is 2 plus 1 plus 1. And this thing has total degree 1. Yeah. So, there are other notions of degree for multivariate polynomials that might be relevant. Like you might just look at the degree in each variable individually. But that wouldn't be called total degree, right? So I'll just mention now, like an n-variate polynomial is said to be multilinear. An n-variate polynomial is multilinear if the degree in each variable is 1, is at most 1. Okay. So like this example is multilinear because, no individual variable has an exponent larger than 1. But this would be not multilinear because x1 has an exponent of 2 here, which is bigger than 1. So no, multilinear is referring to degree at most 1 in each variable, but the total degree of a multilinear polynomial can be up to, if it's in n variables, can be up to n. So the total degree of an n-variate multilinear polynomial can be up to n. Right, but so here is a 3-variate multilinear polynomial which has total degree 2, but if I added to this polynomial, another term, and that term was, say, if I added in, 3x1 times x2 times x3, now the total degree would go up to 3. And the point is, this has degree 1 in each variable, but there are 3 variables. So, the total degree, of something that has 3 variables and is multilinear can be up to the number of variables, which is 3. Okay, so yeah, mostly total degree is what's going to matter. But the property of a polynomial being multilinear is a property of the degree in each variable. the total degree can be up to the number of variables for a multilinear thing. Okay, so with that out of the way, I can give you the Schwartz-Zippel lemma. It's now also attributed to DeMillo and Lipton, who I think they prove something weaker than Schwartz-Zippel, but they did it earlier than Schwartz-Zippel. Anyway, so Schwartz-Zippel says, suppose G is an n-variate, and n is not going to matter, but just say it could have any number of variables, polynomial, over some field f of total degree at most d. Then if let's say that the probability, if I choose an input r to g at random from field to the n, so the probability that g of r is 0, well, let's say it's a non-zero n-variate. So if I take a non-zero n-variate polynomial of total degree at most d and I evaluate it at a random input, the probability I get out 0 is at most the total degree over the size of the field. And an equivalent way of saying that is if G and H are two different n-variate polynomials, both of total degree at most d, and they're not the same polynomial, then if I evaluate them both at a random point, the probability they agree at that point is at most the total degree of both of them over the size of the field. Okay, and the point is that if G and H are not the same polynomial and they're both of total degree at most d, then their difference is a non-zero polynomial also of total degree at most d. If then I can apply my first formulation of Schwartz-Zippel and get the conclusion down here. Their difference is 0 at R if and only if they evaluate to the same thing as R. So talking about the probability two different polynomials agree is the same as talking about the probability a non-zero polynomial spits out 0 at a point. And so this is a multivariate analog of the fact of the very simple univariate fact that any degree d univariate polynomial that's not the zero polynomial has at most d roots. Right. So, if n was 1, this statement here would be, equivalent to the fact that a univariate polynomial of degree at most d that's not the zero polynomial has at most d roots. So you should think of this as just a generalization from univariate to multivariate of that basic fact. And when you start talking about multivariate polynomials, like the relevant notion of degree as far as Schwartz-Zippel is concerned is the total degree. Okay, so that's Schwartz-Zippel. Okay, questions about Schwartz-Zippel?
I have one, maybe it's stupid, but just for the intuition. If this random value would be the same for each of n variables, how would it differ things? What would change?
Interesting. So you're saying, if suppose rather than all entries of R being, so rather than here, let me put an arrow over it. So you're saying suppose R arrow was R comma r, n times
Yeah,
for a random r.
yeah, yes.
Okay, let me just think for a second. Probably everything should completely fall apart and you get horrible guarantees. Let me just think. Um, mm, let's see. Yeah, so let's consider g of x1 comma x2 as x1 minus x2. Then g of r comma r is 0 for all r. Yeah, so it's like a total failure of Schwartz-Zippel in that case. So Schwartz-Zippel, it's like really important that there is a generalization of what I just wrote, but what you just described is not doesn't work as a generalization. So the right generalization turns out to be you need product sets. So so by S to the n, I mean S is any subset of the field and S to the n is the product set. Like S by S by S n times. And then Schwartz-Zippel does hold, and size of field just gets replaced with size of S. But if you don't have independent coordinates of R, so if you don't have R chosen from a product set, as this shows, that you can get probability 1 that the non-zero, that g of the quote random input is 0, even though g itself is not the 0 polynomial and has very low degree.
That's great for the intuition. Thanks a lot. Am I correct that one of the examples for this product sets is powers of tau, powers of r that we saw earlier?
No, so powers of a single R would not be a product set. That would still be like so a product set would be like, I don't know, like S is 1, 2 up to, I don't know, like a million. And then every entry of R, each entry R being chosen from the product set S to the n means each entry of R is uniform, random from S. Whereas if you set R to be powers of a single R, as soon as it's not like all of the entries are extremely correlated with each other, right? In fact, once I tell you little r, I tell you all of big R. So this would not be drawn at random from a product set. And I think you also would have a complete failure of Schwartz-Zippel if you chose R in this way. I think you just have like g of xy is like well, let's say g of xyz. No, let's do it xy. Like is one. Let's say even 1 minus y, right? So then if you set xy to be 1 comma r. No, I messed this up. 1 minus x, that would certainly mess it up. If you set then g of 1 comma r is just 1 minus 1, which is 0, for all x of this form. And you can come up with similar things. If you g of xyz. Let me just so if you set xyz to be 1 comma r squared, where r is random, but g of xyz is let's see, z minus y squared, like that'll you'll get the failure again, right? Because if I feed into z minus z, if g of xyz is z minus y squared, and I feed into it 1 comma r squared, I get r squared minus r squared, which is 0. So this product set situation seems really intrinsic to Schwartz-Zippel working, and it does work for every product set. But once you have correlation between different entries of R, Schwartz-Zippel is sort of out the window. And hopefully these examples, capture, like why Schwartz-Zippel, like you just can't hope for something like it to hold unless the input is chosen at random from a product set.
Yes, and it seems to me now that roots of unity wouldn't do it either. So, is there an affordable for this lecture an example of this of a product set?
So yeah, I guess my general sense is all of the examples you're raising come from univariate land, and I think Schwartz-Zippel basically fails for these examples exactly because multivariate polynomials and univariate polynomials are different. So I'd put it that way. As we'll see soon, possibly even next week, we'll start seeing interactive proofs based on multivariate polynomials, and you'll see the verifier winds up picking random challenges that come from product sets. I mean, actually, it's just it's just the whole field, field of the n or whatever, and I think that's very natural. That the verifier's challenges come from these product sets when you're dealing with multivariate polynomials, whereas all the univariate snarks, you see roots of unity and stuff like that coming up over and over again. And again, that's natural in the univariate case. But yeah, I mean, Schwartz-Zippel is basically a statement about multivariate polynomials, and product sets and multivariate polynomials go together, very nicely. Is I guess the most I can say about it right now.
Thanks a lot for this intuition. We'll pay attention to it further.
Yeah, great. Thanks for the questions.
Yeah, can
Another
I just
question?
point out? Yeah, I just wanted to ask because right. So you just showed why this doesn't work, but I think in certain literature about lookup tables there is a mention that you can get multiple random variables by just grabbing a pair of random variable, but here it doesn't work because those random variables need to be independently sampled across different dimensions of the multivariate polynomial, whereas here by using the random variable, you sort of collapse the dimensions of the multivariate polynomial.
Yeah, that's exactly right. So, I mean, I actually think often of univariate polynomials. Univariate polynomials are a special case of multivariate ones. And like in some sense, that's that statement is trivial because a one variate polynomial is a multivariate polynomial, with one variable, right? It's an L-variate polynomial where L equals 1. But more than that, like, if you have a like an n-variate monomial which products out n variables, and let's say this is g of x1 to xn, and if I do wind up, as you're noting, feeding in the same value to each of those n variables, I just get out r to the n. And so often it's the case, like if you design a protocol targeted at multivariate polynomials, you get out like the protocol also works for univariate polynomials as a special case, just by, because you get out a univariate polynomial just by feeding in the same value to each of the n variables of the multivariate thing. And so that, yeah, I mean, that's worth keeping in mind, but like Schwartz-Zippel will totally fail if you try to do something like this. You just can't apply Schwartz-Zippel to analyze this kind of thing. And let's see, do I want to say anything else about that? No, I'll just leave it there. Yeah.
Professor, I had a quick question. So if S as defined above in the notation, in your
Yeah.
this S and if this S and the roots of unity cannot behave as a sampling set for Schwartz-Zippel, then how is Goldilocks fields working to support as the sampling set for Poseidon hash that I think we have talked about prior?
Well, for Poseidon hash, by the way, so this, you can take a tensor product of this S, and that would work for Schwartz-Zippel, right? So if G has n variables for whatever n you care about, total degree D, then the probability if you pick R from this S to the n, say G is not the zero polynomial, that G of R equals 0, like that will be at most size of the D over the size of the set, which is 2 to the 20. So this does work. This kind of, you can take any S, and what's as long as you draw R, each coordinate of R independently from S, you do get a Schwartz-Zippel statement that works with the denominator in the probability being the size of the S. Now, as to your question of if what if your field is the Goldilocks field, and your S is even the whole field, so that the Goldilocks field has size about 2 to the 64, and you do get failure probabilities when you work over the Goldilocks field of roughly 2 to the minus 64, okay, which is not cryptographically low. And that is something that any snark designer that works over the Goldilocks field has to deal with. And typically the way they deal with that is when you do ultimately apply either Schwartz-Zippel or if you're dealing with univariate polynomials like the univariate analog of Schwartz-Zippel, that any degree D polynomial has at most D roots as long as it's not the zero polynomial. Basically what they'll do is they'll when that statement is applied, they will not use Goldilocks itself. They'll use like a degree 2 extension field of Goldilocks. Okay, so that's really the answer to your question. If you want to apply something like Schwartz-Zippel, R is chosen at random from F to the N. And look at, the probability that like G of R equals H of R, when G and H are not the same polynomial or something, and say this is at most, the degree of G and H over size of the field, they'll make sure that the size of this field is like 2 to the 128. So, if you use, Goldilocks itself has size 2 to the 64, but a degree 2 extension of Goldilocks has size 2 to the 128. And then this probability will be cryptographically low. So the Poseidon hash, I think Poseidon is defined over Goldilocks itself, not a degree 2 extension of Goldilocks, but it's meant to be collision resistant. I don't have all the details cached here. So either they're not applying this sort of statement over Goldilocks directly, or somehow the collision resistance, rather than some kind of information theoretic analysis of Poseidon is coming up. I don't think I can say more than that online. I'd have to go back and look in more detail at what Poseidon is doing. I can speculate. So don't quote me on this. I think normally, I think Poseidon would be used to hash like I don't know what it like 8 Goldilocks field elements, to 4 Goldilocks field elements or something like that. And then yeah, they're like, it's not a degree 4 extension of Goldilocks, but still the output space is 256-bit output space. And so if you find two inputs to Goldilocks that agree on 3 out of their 4 outputs but not on the 4th, like that would not be considered a collision. So you still have the case that again, I'm speculating here. I don't. I'd have to look at how Poseidon works, but that may be another way to get around this issue that 2 to the 64 is simply too small a field to get any kind of cryptographic security out of that field directly. Yeah. So hopefully this rambling made some sense.
Yes, sir, it did. Thank you, sir.
Great. Okay. More questions?
I have a question about the question you answered before.
Okay.
I think the reason that it doesn't work because if we plug x in every variable xy, xi, it will be, if the polynomial is 0, it's okay, it doesn't work. But if the polynomial is non-zero, so the degree of this polynomial will be at most d, or the number of variable if we have n variable. So I think we can apply the Schwartz-Zippel lemma to this polynomial, because if the polynomial is non-zero and have a degree at most d, so we have the Schwartz-Zippel lemma. I think the reason, I don't know, I have to check, but I think the reason doesn't work because the polynomial is 0 when we plug x in each variable x, and this is I. What do you think?
Well, I think that maybe I misunderstood which example we were discussing here, but I think the failure of typically if Schwartz-Zippel like doesn't apply in a given setting, it's because you're not choosing the coordinates that of the random input that you're feeding the polynomial from a product set. So you have correlations between coordinates. That's normally like the source of failure of Schwartz-Zippel. I shouldn't call it failure, like it just doesn't apply to that setting for inherent reasons, right? So this polynomial here, it has total degree 1, right? So it's absolutely the case that if I pick two random coordinates r1 and r2, and I evaluate g at those coordinates, you're very unlikely to get 0, right? Schwartz-Zippel does apply. The problem is if I choose R2 to equal R1, R1 comma R1, then deterministically it will spit out 0. So if the two coordinates are chosen independently at random, you're good. Schwartz-Zippel applies. If they're chosen in a correlated manner, as here, the Schwartz-Zippel doesn't apply at all, and it can't apply because this thing has very low degree, but spits out 0 at any input of the form R1 comma R1.
That's it, because this polynomial, when we plug x in the two variable, we will get a 0 polynomial. But
I
if
see
we
what you're
have
saying.
variable
Yeah,
x, y,
that's right.
well,
That's right. That's right.
I think this condition can help. I don't know. I have to check, but I feel like, because we will get at the end, we will get a polynomial of degree
Yeah, I think you're right. And
of a
actually,
polynomial.
yeah. So we're not going to care like how Schwartz-Zippel is proved. We're just going to use the theorem as a black box. But actually, the standard proof of Schwartz-Zippel does some kind of reduction from n variables down to 1 variable, and evidently that reduction can fail completely if so I think you're basically capturing how the proof of Schwartz-Zippel actually works, and there's probably just one failure case, which is when you collapse n variables down to 1 in some way and you get out the 0 polynomial, then you have no conclusion to draw. Okay, good.
Yes, right. Thank you.
Yeah, no, thanks for weighing in. Yeah. Other questions? Comments? All right, so just a quick, variation of Friedwald's algorithm, which actually this is Friedwald's algorithm. If you let x be n random values, R1 to Rn, each random from the field, and let's say C does not equal A times B. Then the probability that Cx equals A times Bx is at most 1 over size of field, which compares favorably to what we saw before, where X was powers of a single random R, where the failure probability was n minus 1 over the size of the field. And the proof of this is, that if you look at the ith entry of Cx, this treats, so it treats rho I of C as an n-variate polynomial of total degree 1, also known as a linear function. Right, because the ith entry of Cx is sum over I equals 1 to n of, j equals 1 to n of Cij times xj, right? And this function is total degree 1 in X. Okay, and so if rho I of C is not equal to, entry by entry equal to rho I of A times B, then, CXI is, if we compare the ith entry of CX to the ith entry of A times BX, the ith entry of that, what we've done is we are evaluating, two different, total degree 1 polynomials at a random input X in field to the n, and so you can apply Schwartz-Zippel to conclude that, if I evaluate two different functions of total degree 1 at a uniform random input from the whole field, Schwartz-Zippel says that, the probability that they agree at this input, that let's call the polynomials, I don't know, P and Q. The probability P of X equals Q of X is at most the total degree, which is just 1 here over the size of the field. Okay, so so you're seeing it's not really a major benefit if you're working over a big field, if n is 2 to the 20 and your field has size 2 to the 256, who cares, about the difference between a failure probability of 2 to the minus 230 versus 2 to the minus 256 or whatever. They're both astronomically small. Like you'll never see a failure. But still, it is an improvement. So you are seeing, n varied polynomials sort of being better in a sense than univariate ones, and why it's because where is the betterness coming from? It's because with n variables, the total degree, of the functions we're analyzing can be just 1. With univariate polynomials, we need, degree n. Okay, and we'll see, this sort of phenomenon come up over and over again in the coming weeks, because we start, I'm going to start covering interactive proofs, which tend to use multivariate polynomials and, the sum check protocol and all of that. All of the power of that, as we'll see, sort of comes in because the total degree of n varied things can be lower than the total degree of univariate things of the same size. Like a size n univariate polynomial is like degree n, but like a size n polynomial in many variables can have much lower total degree than n, and the statements I'm making will be made precise soon. Okay, so that's Schwartz-Zippel. Let me just check on the time and see if anyone wants to ask any questions about that. Questions? All right. Okay. So now I want to talk a little bit about error correcting codes and cover univariate Lagrange interpolation, which I am running behind as usual, but I'll try to do this expeditiously. So let me just remind you briefly about Reed-Solomon fingerprinting. So here, Alice and Bob had two large vectors, X and Y, and they wanted to know, does X equal Y? Okay, and the way the protocol, the Reed-Solomon fingerprinting protocol worked was X was interpreted as a univariate polynomial. So interpret X as a univariate polynomial P of Z, whose coefficients are the entries of X. Interpret Y as a univariate polynomial Q of Z, whose coefficients are the entries of Y. And then Alice just picked a field element at random and sent to Bob R and P of R, and Bob, checked whether Q of R was P equals P of R, and he said, if they agree at R, then I'm going to assume they're literally the same polynomial. Okay, and so there's a one way of describing what P of R is the following. So I'm going to it's just a change in perspective. So you can think of P of R as a random entry in what's called the Reed-Solomon encoding of X. Okay, and so let me describe what that means. So a Reed-Solomon encoding is a specific error correcting code. So error correcting codes come up over and over again in Snark design. And the idea of an error correcting code is you have some message X. Actually, in coding theory, people call this M for message, but in the fingerprinting example, I called it X. And what a code will do is it will take the message and encode it to get out what's called a code word. So we can call you might call it abbreviate this enc of M, but not this enc is not encryption. It's encoding of M. And so if this message has n field elements, this code word will have more than n field elements. Okay. And so you think of the code word as like it's adding redundancy. Yeah. So like it's taking a message of length n and turning it into something much longer. Okay. And the idea of what's really important to snarks, this word correcting and error correcting code gets a little confusing in snark land. What snarks really need, snarks do not need error correction typically. What they need is what I call distance amplification. Okay, now distance amplification is sort of, it's necessary, but not sufficient for correcting errors. I'll tell you shortly what correcting errors means. But they go hand in hand. So typically, if I give you like a distance amplifying code, it's also an error correcting code. So what do I mean by distance amplifications? I mean, suppose you have two messages, M and M prime, that differ, that they're not the same message. So they differ in even just one entry. So they're just not the same message. Okay, distance amplification means that the encoding of M will differ almost everywhere. So we require that the encoding of M at most entries is different than encoding of M prime at the same entry. Right. So you take two messages and maybe they're the same message except for one spot. Maybe this is the only spot where they differ. Okay. And if you then look at the encodings, distance amplification means, their encodings, an encoding might be like a much longer vector than M itself. Their encoding should differ almost everywhere. So, a large fraction of the entries of the encodings, differ. So all of these dots I drew are differences. Okay, so that's what SNARKs needs, is this distance amplification property. And intuitively, the reason we need them is because the whole point of SNARKs is to make sure the prover is totally honest, right? If the prover says, "Hey, like I ran this computer program on a witness, and the computer program spit out, except," we really need that if the prover deviated from what it was supposed to do at like even a single step of running the computer program, that the verifier is going to detect the deviation and reject the attempted proof with overwhelming probability. So we really need that even tiny differences, running the computer program completely correctly versus running it completely correctly, but for one step, out of trillions of steps or something. We need to blow those tiny differences up into very easily detectable differences, so that even though the verifier is like really fast and the proofs are really short, we still nonetheless have the verifier detect the deviation efficiently. And that's exactly what distance amplification properties of error correcting codes gives, where even one tiny difference gets blown up after you do the encoding into very easily detectable differences. So what's happening in Reed-Solomon fingerprinting is, the
Excuse me,
encoding.
can I ask a quick one?
Yeah, go ahead.
A good hash algorithm have the same property. Am I correct that with error encoding we need that it is reversible?
Let me think for a second. Good hash. So you're proposing that you take a message M and the encode, you would interpret M as the description of a hash function?
I mean this one bit difference and distance amplification. It's a characteristic of a good hash function too.
Oh, I see what you're saying. Yeah, let's see. So there's the question of the issue with the hash. You're right that a hash function, if you hash two messages, so this is a hash function. You're right that if M and M prime differ in even a single entry, then with a good hash function, the hashes will differ. Like with overwhelming probability, or maybe there's it's a cryptographic hash, and there's a computational hardness statement one can make about this. Instead, the issue is that the hash outputs are typically pretty small, maybe 256 bits, and so it's it's related. Good hashes are somewhat related to error correcting codes, but they're not the same, because an error correcting code turns the message M into a much bigger object, a whole code word, and a hash actually does the opposite. It's compression. it's literally the opposite. It compresses M down to just 256 bits. And so it's similar, that if two messages differ in even a single coordinate, the hashes should differ and the encoding should differ, but it's not the same. Here the encodings differ at almost all entries of the very large encoding. Here, the hashes differ, but the hash themselves are so small. There's no distance amplification happening. Does that clear things up? Does that make sense?
Yeah, but I believe the question was whether the mapping and error correction code is bijective, whether you can recover the message from the encoding. I
Yes.
believe.
Yeah.
Yes.
Great. Yeah. So I guess it would be injective. Just because okay. Bijective if you restrict your attention just to code words, which by definition have some message that maps to them. Yeah. So I mean, for most error correcting codes, if I give you the code word, you can efficiently tell me the message, that produced the code word. In fact, what the meaning of error correction? So again, the correction is never actually really needed in Snark design, with some caveats, but I'll elaborate on that in a second. Error correction means, like, if I give you even a corrupted version of the encoding of M, you can quickly figure out M. Right. So the question, that was just asked was, if I give you the actual encoding of M, can you figure out M? And with good error correcting codes, not only is the answer to that question yes, the answer is still yes, even if I took the encoding and I took like a relatively small fraction of entries of the encoding, the dots I just drew, and just corrupted, changed them, however I wanted. Like, then I could still, can still identify Emma efficiently.
So we care about the size of the result and maybe about computational complexity, the resources that takes to get the encoding.
Yeah,
Am I right?
exactly. So okay. So in Snarks, well, okay. So there are a bunch of caveats which will become much clearer, like, as we go through this study group. So,
Mhm.
okay, some comments. So what in Snarks, often no one, not even the prover, ever materializes the entire encoding, and I'll explain what that means in a second. So the encoding, of some message might be enormous, might have size, like field size to the, circuit size, where the circuit is, what you're proving, a satisfying assignment to or something, so like just astronomically big, like vastly bigger than like the size of the universe or something. So no one could ever write down the whole encoding, but no one will ever have to. And so that I can explain in a moment. But then even in settings when someone does have to write down the code word, when someone does write down the whole encoding, and this comes up specifically in certain polynomial commitment schemes like Frye, Laharo, Breakdown, Binius, etc. When someone does write down the whole encoding, no one ever decodes. So in this case, like, we do want, good, like, fast encoding, because the prover is going to have to write down a whole encoding, but we don't really care about fast decoding. Okay. And so it's sort of fun. So, a lot of the codes that people use in Snark design do have fast decoding, but in some specific settings, really just breakdown, we actually use codes where there probably is no efficient decoding procedure, and it doesn't matter really, because no one ever has to decode. Now the caveat is, there's something called knowledge extractors, which, no one runs in the real world. They're purely part of the security proof. And, having fast decoding, can make the knowledge extraction simpler, but like, again, just ignore those. That's an advanced statement that we don't need to worry about now. So yeah, these are funny caveats about error correcting codes, how they arise in snark design. Often no one writes down the entire code word at all, so the encoding can be huge and it's okay. And then sometimes people do write down the entire code word, but when they do, we don't worry about, no one ever has to decode. So yeah, in some cases, we don't even care about fast encoding. In other cases, we do, but even then we don't care particularly much about fast decoding. Okay, I hope this discussion has been fruitful so far. Does anyone want to ask more questions?
Brilliant explanation. Thank you.
I wanted to ask a quick question, Professor. If the property we need from the error correcting code is that it is expanding and it is bijective, then is there any reason why any normal secret key based CPU security encryption scheme is not used? Is it because it's an overkill?
So I'd have to think about it a little bit. But one thing I can say is that encryption it would typically be much slower than encoding with an error correcting code. So, like, let's say we're about to see some examples finally after my rambling, discourse on error correcting codes in general. So typically taking a message and computing the encoding under your favorite error correcting code of M would be much faster, or is faster than computing the encryption. And here it's really bad that I'll write it out. Encoding encryption. It's too bad they both start with enc. For typical crypto systems. So typically the codes we use, like encoding just involves finite field operations, whereas encryption might involve cryptographic group operations or something else. And so that's one reason, is just like the performance is probably better by using an encoding instead of an encryption. But the other thing I'd have to think about, which is probably not a big deal, but is just with encoding, the security of the snarks is going to rely on the fact that if I take any two messages M and M prime that are not the same, and I look at their encodings, that for sure that, so if M does not equal M prime, then enc M disagrees with, enc M prime, in at least, it depends obviously on the code, but let's say at least 3/4 of coordinates or something. And with encryption schemes, I'd have to think about whether they actually have that property or not. Yeah, I just it probably only take a second of thought, but I don't even want to try to do that online. Encryption schemes are just different objects than encoding schemes. Does that make sense?
So the property that you just told in the end, that property is going to be offered by even a standard CPU security. So I believe the fastness of the procedure is the only point I could extract out of what you said.
Okay, yeah, I get that's probably right. if the encryption scheme is compressing, that if you encrypt a message, with a trillion, entries, and you get out one or just a couple of group elements or something, if it's compressing, like big messages mapped to small ciphertext, and again, I'm revealing how little cryptography I know, right? Like I don't even know if this is the case or not with standard encryption schemes. But then you literally cannot have this property, right? Just information theoretically, large distance of an error correcting code relies on the code being, what's the opposite of compressing? Expanding? I don't know. Whereas if encryption scheme is compressing, it just can't have good distance information theoretically. any distance that's there is really computational, just like with Merkle hashing or something. If Merkle hashes are only 256 bits, no matter how big the thing you're hashing. So of course there are lots of messages that hash to the same thing, but it's believed to be computationally infeasible to find those messages even though they exist. So that's a caveat. I actually don't know offhand if standard encryption schemes are compressing or not.
Thank you.
Great. More questions? All right. Okay. Good. So let's talk about some specific examples, and I'm going to try hard to wrap up. I think I'm going to skip Lagrange interpolation today since I'm so far behind, and my kid is sick and home, and I'm going to get in trouble if I take much longer today. So, yeah. So let's just. I guess what I want to cover. I guess I'm going to describe the Reed-Solomon code. And how it arises, in Reed-Solomon fingerprinting, and then I'll talk about the low degree extension code, and then we'll wrap up. And these are closely related codes, and in fact, in some sense, they're the same code. So I'll discuss that now. Okay, so Reed-Solomon code. You have a message M, and so this is the Reed-Solomon RS code. You have a message M. Okay, so somehow you interpret M as say M is in field to the n. Interpret M as a degree n-1 univariate polynomial P. And then the encoding of M is just all evaluations of P over some specified domain. So it would be P of x1 up to P of x capital N for and the domain here would be x1 to x capital N. And so fact with if M does not equal M prime, then the encoding of M and the encoding of M prime differ in at least what would it be? Capital N minus little n minus 1 entries or something. And this is just a reformulation of the fact that any two distinct degree n-1 polynomials agree at most n-1 points. Okay. And yeah, so in Reed-Solomon, we sort of already discussed this, but the only question that I've left sort of unspecified or unanswered right now is how do you interpret M as a degree n-1 univariate polynomial? Okay, and yeah, there are the two natural ways to do this that we've already discussed is to treat M. So one would be to treat M as like listing the coefficients of P. Another would be to treat M as listing the evaluations of P over what's called an interpolating set. Okay, and so just tying this back to fingerprinting, like where you remember Alice sent to Bob R and P of R, right? What P of R is here, P of R is a random, it's a single random entry of the Reed-Solomon encoding of Alice's input. Okay, and so pictorially, what if you cast Reed Solomon fingerprinting in this way, maybe now I'll call Alice's input M and Bob's M prime. What Alice is doing is she's looking at the encoding of M, where now, where the size of the encoding is massive. It's field size many evaluations of this polynomial. And Bob is looking at the encoding of M prime, right? And Alice is picking a single random entry of the encoding, and she's sending to Bob, the index of that entry and what that entry was. And Bob is looking at his, the rth entry of his encoding and checking whether P of R equals Q of R. And so this is what I mean when I say that in SNARKs, often nobody has to materialize the entire encoding. So here, like if our field has size 2 to the 256, like this encoding is bigger than the entire universe or the number of atoms in the universe or something, and it's no problem because Alice is only ever going to compute a single entry of that encoding, which she can do quickly, and Bob is only going to compute a single entry of his encoding. And so the fact that that if M does not equal M prime, then P of R does not equal Q of R, except with tiny probability. That is equivalent to the fact that the Reed-Solomon code has really good distance. That if M and M prime are not the same, then the encoding of M and the encoding of M prime differ almost everywhere. And yet nobody is ever writing down the whole encoding of either M or M prime. They're only ever looking at a single entry of the encoding. Okay. So there are two more things I want to say. Any questions? Okay. So often no one writes down the whole encoding when you're designing SNARKs. So, but two, if someone did want to write down the encoding, they could, there are algorithms to do that, and so I'll just state that in a second. The last thing I wanted to say was I wanted to briefly talk about low degree extension codes. Okay, and I am at the at the very limit of my time here, so let me just get through this quickly. So we already talked about this. Often no one writes down the encoding. Okay, so let's say, yeah. So I guess I'll talk about these 2 points are related. So let me discuss them together. So let me tell you what is low degree extension code. So the low degree extension code is exactly the code that you get when you treat the message being encoded not as the coefficients of the polynomial in the standard monomial basis, but rather as the evaluations. Okay. And so there, you have this message M, and you treat these as like, the first, say it has length n, the first n evaluations of a degree n minus 1 polynomial, meaning by first I mean over some interpolating set. And then the encoding of M would be evaluations over a bigger set, evaluations of the same polynomial over a bigger set. And people call this low degree extension because, if the bigger set, is a strict superset of the smaller set, so say the interpolating set is S, and here the bigger set is T, and S is a strict subset of T, then this code is what's called systematic, where, the first n evaluations is M, right? So the message itself that you're encoding is a subset of the encoding, but then the encoding adds extra evaluations. It's adding redundancy. Okay. So that's why this would be called the low degree extension code. Right. It's like you think of it as you're taking the message M and just extending it to a bigger vector by evaluating the polynomial corresponding to M at strictly more points. So T is strict, has S as a subset. S is the interpolating set. Now, when people talk about Reed-Solomon codes, they often mean the low degree extension code, but sometimes they might interpret, Reed-Solomon generally means you interpret the message as a univariate polynomial, and then the code word is a whole bunch of evaluations of that polynomial. But they don't. The Reed-Solomon is used to refer to several different ways of going from M to the associated polynomial. So if you want to be very precise about, saying, hey, the way we're interpreting M as a univariate polynomial is to think of M as listing the univariate polynomial's evaluations over an interpolating set, that if you say low degree extension code, it's crystal clear that that's what you mean. If you say Reed-Solomon code, that might or might not be what you mean. Okay, and so the last thing I'll say is with the low degree extension code, like so one, like if T, the big set, is something like roots of unity, so like capital Nth roots of unity in a field, okay, then the encoding of M can actually be computed in order n log n time. Well, let's say n is like 4n or 16n. So it's related up to little n. Capital N is constant factor bigger than little n. Then encoding is n log n time. I guess precisely it would be capital N log capital N time. But if capital N and little n are related by a constant factor, then that constant factor just gets hidden by the big O notation, and we can just use little n rather than capital N. This uses FFTs, fast Fourier transforms, which we talked about previously. So it only works over some fields. Basically, not all. It works whenever you have like roots of unit. The set of roots of unity, in the field that you want to use actually exists. Some fields just don't have a nice set of roots of unity. So that means, like in Frye or Lajero, when the prover actually does need to compute the low degree extension encoding of M, it can do it in quasi-linear time, n log n time. Okay, so so Reed-Solomon encoding is efficient. Now, of course, that statement only makes sense if the code word is not that much bigger than the message, right? If the code word is bigger than the size of the known universe, then no one is going to write down the code word, even if it has quote efficient encoding. But yeah, so Reed-Solomon codes have efficient encoding as long as the length of the code word is within a constant factor of the length of the message. And let's say if you use the low degree extension code and you only want to compute the low degree extension encoding, so P is the low degree extension encoding. But this is with univariate polynomials. If you only care about one entry of the encoding, you can do that in order n operations. So there's no you don't need FFTs, you don't get this log n factor, and this is called univariate Lagrange interpolation. Okay, this is what I wanted to talk about today, but then took way too long, and we're not going to get to it, but I'll discuss it next week. So, but I'll just tell you what this is. Like, univariate Lagrange interpolation is the task of going from, a message listing, little n evaluations of P over whatever interpolating set you care about. And for this, it doesn't matter that the interpolating set be root to unity or anything. Root to unity only come up when you need the entire Reed-Solomon encoding, not a single entry of the Reed-Solomon encoding. So if I give you n evaluations of a univariate polynomial P, and you just want to know P of R for a single R, for one input R, you can compute that in linear time. And again, it's called univariate Lagrange interpolation. And that's what I'll start next time by discussing. Okay. Okay, so that's everything I wanted to say. So again, just recasting, the fingerprinting protocol for equality testing of two sessions ago, in the language of error correcting codes, where in this language or viewpoint, Alice and Bob are replacing their inputs themselves with error correcting encodings of those input and just checking whether the encodings agree at a single randomly chosen entry. And by the distance amplification properties of the encoding, if their messages are not literally the same message, then, it's enough to just look at a single randomly chosen entry of the encodings because, if they're not the same message, the encodings differ almost everywhere. That is what distance amplifying properties of the encoding means. Again, this is a good example where, one, nobody ever has to write down the whole code word, and two, we don't actually care about like decoding or error correction. We only care about the distance properties of the code. And again, if you use the low degree extension encoding and you do this sort of thing where you just inspect the encoding at a single random point, you can do that in linear time. That procedure is called Lagrange interpolation if the code you're using is a low degree extension code. Okay, so that's it for today. I will skip questions because my wife is just going to totally murder me already. And I'll take them asynchronously in Discord if you'd like to ask them, or we can discuss them next week. So thanks for joining, and I'll see you next week. Have a good one.